Welcome to our foundational theory session, where we'll explore the systematic backbone that makes machine learning projects successful and reproducible. Today, we're diving deep into the machine learning process overview. Think of this as your comprehensive roadmap for transforming raw data into intelligent, deployable AI systems that solve real world problems. Let me start by answering the fundamental question: what exactly is the machine learning process? The machine learning process is a systematic, step by step methodology that guides data scientists from raw data to deployed predictive models, ensuring reproducible and reliable results. Think of it as a well tested recipe that, when followed carefully, consistently produces high quality machine learning solutions. Just as master chefs follow proven techniques to create exceptional dishes, data scientists use this structured approach to build trustworthy AI systems. Our comprehensive process unfolds across three interconnected phases, each building upon the previous one like floors of a carefully constructed building. The foundation begins with data pre-processing, where we import, clean, and split our raw data into workable formats. This foundation supports our modeling phase, where we build, train, and generate predictions using sophisticated algorithms. Finally, our evaluation phase provides the quality assurance through metrics, validation, and deployment decisions. Each phase contains multiple critical steps, and the systematic execution of these steps separates professional machine learning from amateur experimentation. Data pre-processing serves as the foundation of every successful machine learning project. Much like preparing the ground before constructing a building, you wouldn't build a house on unstable soil, and you cannot build reliable models on unprepared data. This phase transforms messy, real world data into clean, structured formats that algorithms can effectively learn from. The four essential steps: import, clean, split, and feature engineering work together to eliminate data quality issues that could undermine your model's performance. The modeling phase represents the core intelligence building activity where mathematical algorithms learn to recognize patterns and make decisions. This is where theoretical concepts meet practical application, transforming your carefully prepared data into predictive systems. Through model selection, building, training, and prediction steps, we create AI systems capable of understanding complex relationships within your data, applying that understanding to solve real world problems. Evaluation provides the rigorous quality assurance that ensures your model performs reliably in real world conditions. This validation phase goes beyond simple accuracy measurements to provide comprehensive performance assessment through multiple metrics, cross validation techniques, and systematic model comparisons. The final verdict from this phase determines whether your model is ready for deployment or requires additional development work. Understanding why we religiously follow this systematic approach is fundamental to becoming an effective data scientist. This structured methodology provides four critical advantages. Reproducibility ensures other practitioners can achieve similar results. Preventing data leakage eliminates accidentally using future information to predict the past. Fair comparison enables objective evaluation of different approaches, and rigorous validation provides justified confidence in deployment decisions. Our historical journey begins in the 1950s during the Statistical Methods Foundation era, when brilliant mathematicians and statisticians laid the theoretical groundwork that still underlies modern machine learning. During this pioneering period, researchers developed fundamental techniques like linear regression and basic classification methods, establishing the mathematical principles that remain central to today's sophisticated algorithms. The 1980s marked the expert systems and rule based AI era, when artificial intelligence took a fundamentally different approach from today's data driven methods. Researchers focused on encoding human expertise directly into computer systems through explicit logical frameworks, teaching us valuable lessons about capturing human knowledge while highlighting the need for more flexible approaches. The 2000s ushered in the big data and modern ML algorithms era, witnessing the convergence of growing data volumes, increased computational power, and breakthrough algorithms. Companies like Google and Amazon demonstrated how machine learning could operate at unprecedented scale, establishing AI as a practical tool for solving real business problems rather than just academic curiosity. Today's AutoML and deep learning AI democratization era makes sophisticated artificial intelligence accessible to practitioners without deep technical expertise. User friendly tools and cloud platforms are democratizing AI, allowing businesses and researchers to implement sophisticated solutions without extensive infrastructure or specialized teams. Now you got a very good overview of machine learning process overview. In the next session, we will learn about data pre-processing theory. So guys, see you in the next session.